It's my pleasure to introduce Dwayne Miller to you. And I'm also very happy to welcome him here for the physics colloquium, even though he's a little bit of a chemist. He is a Canadian by upbringing, but he did his PhD 1983 at Stanford with Professor Michael Feyer in chemistry. Then he went to Rochester University, where he became an assistant professor, basically after a short postdoc, 84. Then he went up the ladder, the academic career ladder, from assistant professor, associate professor to full professor. And 92, he was basically then the full professor at the university in Rochester. And 95, he moved basically back home to the University of Toronto. And as a professor in physics and chemistry. In 2005, he became a director of the Institute of Optical Sciences. And since July 2010, he is actually now in Europe. He became one of the Max Planck directors and division heads of the CFEL. So it's a joint appointment between the Max Planck and the University of Hamburg and still University of Toronto. And his focus there on the CFEL is on the development of ultra-bright electron sources for structural dynamics. He has won many prizes. One of them is the Humboldt Award, and then the Canadian Research Chair in Femtosecond, and he received also a medal in chemistry from the Royal Society of Canada. So I'm definitely very excited to have him here because he's always still and continues to be very excited about his work. And you will see that during this talk. So all I can say, have fun and enjoy it. Okay,
great.
Thank you very much.
Thanks, Ursula.
Please, Dwayne.
So it's a great, yeah, it's really a great pleasure to be here, one of the shrines of physics, and come and talk about our work, of course. So I had a fun day, and we'll tell you what we're about and give you some idea of the things that are happening now a little bit closer to Zurich. So let me first start off with making the take yours? Okay.
This comes from an experimentalist.
Okay, wow. So making them like your movie. I'll first define my title, which is a little bit odd way to start. But that expression, besides having a nice alliteration, has been used a lot to describe structures that have been captured on millisecond or even microsecond timescales where people say, oh, we have a molecular movie. To me, that's not a molecular movie, that's time-lapse photography. Making a molecular movie is exactly what that means. It means you have sufficient simultaneous spatial and temporal resolution to literally watch atoms move in real time, to see all the correlations that are in a system, right? So if you can do that, you're going to see new things. There'll be some surprises. This is one of the sort of dream experiments in science to be able to do this. And I have to say, if you kind of think about what would be the motivation for trying to push the envelope on this science-time limit, if you're a chemist, and I'm of that tribe, I confess, I actually got a training in immunology, actually, so I'm really more a biologist. But just imagine for this point of discussion, I can watch two atoms fluctuate along a reaction coordinate, and I could witness the moment a bond breaks. I would see the death of a molecule and reincarnation as two new molecules. That's something chemists are constantly trained to think about, right? Now, if you're a biologist, you like to think about structures of proteins or other objects, macro objects, and think about how things sneak into the active region to do work, a biological function. Right? Again, you're picturing motions of atoms, how things fit together. And in physics, of course, if you talk about non-equilibrium electron dynamics, it's the coupling of changes in electron distribution to things we call phonons, and trying to picture how that interaction occurs on there's different kinds of length scales and correlations, right? So any moment I give you those three examples, if you pictured balls and springs moving, you just did the classic thought experiment. You made a molecular movie, albeit in your mind's eye. And for the most part, this was thought to be something out of the laboratory frame. You could never do it. There's a discussion by Eigen where he states explicitly that these are immeasurably fast processes and will always be limited to inferring these details indirectly, right? Now, you can kind of imagine why people might take that stance if you first think about, this is a challenge I gave there's a famous group meeting for the students in the audience. I came after one night of being sleep deprived with my 1-year-old daughter, keeping her up, it was my turn. And I convinced myself we could do this. We had this rushed group meeting to explain how we're going to make a camera. So think about the experimental challenges to make a camera that could make really a molecular movie, right? So the first thing to think about is what's the shutter speed you would need for your camera, right? So if you go back to my canonical example of bond breaking, when you look at a bond breaking event, you have to say, when is the bond broken, right? So take your favorite potential, they're all about the same. If you displace the atoms more than about 1 equilibrium bond length further, the system's no longer bound within kT, and you can say the bond's broken, right? If you just think of this happening at the speed limit, the speed of sound of the atoms moving, that time scale, roughly 1 angstrom divided by the speed of sound of things like you and me is 10 to the 8 minus 8 divided by 10 to the 5th. You get 10 to the minus 13 seconds. That should be fairly familiar. If you look at unimolecular reaction theory, the Arrhenius prefactor is 10 to the 13, right? You can do a better job with transition state theory. It always involves the most strongly damped modes, which are right at that boundary between inertial and Brownian motion, which is damping, and that's 100 femtosecond. That's the time scale of chemistry, right? So if you want to do this on the time scale I'm interested in, you need about roughly 100 femtosecond time scale. 1/10,000,000th of a millionth of time scale. This seems incredibly fast, but I mean, I'm here in one of the capitals of attoseconds. So this is not a problem. You can literally buy a laser that'll give you 100 femtosecond time resolution. The real problem, as all good directors know, to make a great movie, you have to catch the actors in the right lighting, right? In our case, the actors are the atoms. And you have to be able to measure their distances, which means you're stuck with carrier frequencies on the order of the interatomic spacing, or angstroms, which limits you to either hard X-rays or electrons of a certain energy, to use the de Broglie wavelength, right? So this work I'm going to talk about was done in Canada. And so Albert gave a talk before me, so also Canadian. It was like the Canada Day today. So there's this edict in Canada, we believe in funding science so much. Albert's heard this joke many times. We're willing to put thousands and thousands of dollars into it, right? So Canada's not going to be building an X-ray source. So we have to do this with electrons. And so the students in the audience, you can kind of imagine my group talking about, well, yeah, we need 100 femtosecond bunch of electrons. And I'm going to explain to you, intensity really matters. This is a key parameter that was missed. How do you get enough electrons on a 100 femtosecond bunch and avoid electron-electron repulsion? It was thought to be absolutely impossible to ever do this with electrons, right? Well, in fact, we actually were the first to pull this experiment off. And so it's now almost exactly 10 years to the day that we did this. And for the students, again, welcome you to my lab. We'll fly back 10 years. And imagine it's 2002. It's 2 in the morning. This is our first movie camera, 3rd generation electron source. For scale, it's roughly the size of a football, right? And the way this works, so everything I talk about, I'm going to explain how this experiment works in this night that we saw this happen in one shot, and you'll get the rest, right? So our sample sits right there. And you have to bring a laser beam in to trigger the atomic motions because our actors are lazy, right? Like, for example, I know there's a lightning that'll strike over there sometime, but I don't know when to pull the trigger. This is a rare event. So what you have to, so everything I talk about are non-equilibrium dynamics. I have to come in, trigger a structure change, bond breaking process, or whatever this problem of interest is. And then what we do is we bring perfectly synchronized a UV pulse in here and hit a photocathode, and through the Einstein photoelectric effect, we get a replica electron bunch. And then what happens is you simply come and you hit your sample and you see this splash. And to me, this is one of the most beautiful manifestations of quantum mechanics there is. It looks like you threw a rock into water and you see this wonderful ripple, right? So now imagine, and the way you do the way you make the movie, just so this is clear, I'm pretty sure most people understand how to do this, but we do a stroboscopic approach, right? So you come in, you hit the sample, and then flash. You hit the sample, and you wait a little bit longer, and then flash, and you collect a series of time points. I'm a professional, right? You have a series of time points that you can literally pin together a movie. Now imagine you're in my lab at 2 o'clock in the morning, and you're looking right here, and we had this very cheap CCD camera, I have to say, and you're looking at these ripples, and you're watching these ripples. This is polycrystalline aluminum, so that's why it's a ripple pattern. You're watching these ripples move, And if you can do a sine transform in your head, you know you're looking at the change in interatomic spacing, right? And if you look at the clock, the time delay between the pump and the probe, we finally beat this 100 femtosecond limit, and we're literally watching bonds break in real time. This is one of the most exciting moments of my life, and I have to be careful that I'm married. I have 3 kids, all very big, right? But this still gives me a nice warm glow when I talk about that moment. It still sustains me, right? So now again, to add some social dynamic to this for the students here, this famous, in quotation marks, group meeting was 1989 when my daughter was 1 year old. It took us 14 years to get our first paper, right? So be glad you weren't in my group, right? So this was a very long research campaign, many dead soldiers along the way. Okay, these are the guys who survived the march. And I have to tell you, Martin Asherman used to be at the ETH. He started this with me. So the people who started and say died on the way did okay, right? Charlie Schmutmar's at Yale. Martin Asherman was here for a while. Now he's at Kaiserslautern. Okay, so this is my present group here, and I'll explain. I'm going to tell you a few stories and some movies to give you an idea of the scientific impact this new field, this emerging field, is going to have. And I know here this is no stranger with Swissfeld coming up, so I know a lot of people know about this, but maybe not everybody. But I want to give you a scientific perspective that's probably unique to our program in Hamburg and Toronto. So there are 3 stories I'm going to tell you. The best movie we've made, I'm going to talk, is a collaboration with Koshihara's group in Yamauchi, and that one I really want to show you at the end for sure. So if I lose time like I usually do, we're just going to skip right to that one, right? And then we have a wonderful collaboration with Carol Morrison's group on a ring closing reaction. This is conserved stereochemistry. And then what got me to Hamburg is this wonderful collaboration with Klaus Floatman and people at DAISY, where I'll tell you what that other part of my title is, REGAE has to pertain to, but that's what got me to Hamburg. Okay, so this I show you to get across the distinction between time-lapse photography and real movie making. This are 2 time points, point 1, point 2, from the first movie documentary ever filmed, which was also in Canada in 1921 by Robert Flaherty, where he captured an indigenous people, the Inuit, before Western civilization screwed them up, right? And so just for the sake of suspense here, imagine you're an archaeologist or an anthropologist, and you're trying to understand how the Inuit people can survive in these inhospitable climates in the north, right? And the key, their lifeline, is this thing called a kayak. And you're trying to understand the structure-function relationship of this and its people, right? And you have these 2 time points of data. So think about what transpired between those 2 points. Come up with a model. Time's up. You have to publish. I guarantee you, whatever you think happened, you're dead wrong. And this is going to be a theme in my talk, that once you see all the details, previous preconceptions get a bit changed, altered. So let me just show you this movie. So here it is, and this is one of the movies, 10 movies you should see in your lifetime. Right away you see when you have enough intensity, that's not a dog. There was a dog in the second frame, right? That's his son. Nanook is here. And you have to realize the Inuit people do not swim. It doesn't do you any good, it's too cold. So this shows you incredible confidence in this craft where they bring all the food they need for 8 months to their village, right? Because you already see a problem with your model. And you already see the importance of intensity. There wasn't quite enough light in that first frame to see it. And so you were tricked. Okay, so there's his son. This is rather, people complain this is too slow, so I could speed it up. But when I saw this the first time, I actually have an anthropology degree also. So that's his wife. And I should tell you, the women, well, you can watch this. I'll tell you another interesting aspect of this movie. And again, it's really, if you can get a chance to see this, you should. It's marvelous. It's really recorded history. Inuit women never were on a hunt. They only had oral tradition. They have a movie of a hunt, and women came from dog sled 7 days away to see it, and were part of it. It was really, it's quite a remarkable achievement. So that's a baby. It's not over yet. Here comes his daughter. Right? So have you ever seen the Shriners Circus act where the clowns come out of a Volkswagen? It came from this movie. And then there's one more. And there you go. So now you see everything. And what you learned, if you just think about this and reflect for a little bit, the Inuit don't swim. The craft, I won't go into the details of how they do this, is incredibly stable, can haul enormous amounts of weight, and you could have probably guessed that, but you learned something you could never have guessed that's inherent to how they survive in the North. They have an absolutely fantastic sense of humor. They stage us. This was a joke. And the reason for that is you can't dwell on hardship. You have to just move on. So they make a joke of everything. They're practically the funniest people in the world, right? So you learn something very interesting if you see all the details. Now I want to invite you to my favorite part of the universe. I'm zeroing into each and every one of you by a factor of 10 to the 9th, and I'm capturing this special moment in space and time that chemists call the transition state. And what I've done is I've modeled the heavy atoms here as star-like objects, and this giant red star is supposed to be iron, which binds oxygen in hemoglobin in your body. And you'll see sneaking out of the picture right here is diatomic oxygen. And what I've tried to do is capture this moment when a bond breaks, where that stored chemical potential is released as a supernova event. And what happens in each and every one of you, as I'm speaking, hopefully is happening in each and every one of you, this energy is converted, transduced, and causes this entire night sky to rotate to do work on the surroundings and control oxygen inside your body. And if you look at this, this is the dream I had in 1989. This is the problem I'm after. If you look at this, Mother Nature really understands quantum mechanics. You have a quantum singularity, a bond's being broken. You have enormous numbers of degrees of freedom that have to couple to the mesoscale, which is the continuum limit. Nature really understands quantum mechanics. She grew up with it. And she really understands the correspondence principle in ways that we are only now starting to get a hint of, right? And we kind of fool ourselves that we understand things. It's not till you see it in a different perspective that you can kind of appreciate how amazing this event is. Okay, so how do we understand this? And so now I'm going to give you basically the science case for what we're doing. And I'm going to fall short of it. And so you have to cut me a little slack because we're very close to accomplishing this goal. But this has been almost 30 years of my life devoted to this problem, right? So here you have hemoglobin. 4 proteins in a quaternary complex. One chemical bond broken triggers that entire molecule, huge molecule, to undergo a 15-degree rotation and a 6 angstrom translation involving some 10,000 degrees of freedom, marching to one chemical bond break, right? So how do we understand? How do we understand why that structure, like the kayak, has the form it has? And there's so many degrees of freedom, it's impossible to imagine exactly how those forces are orchestrated. So you do the typical physics thing. We break this up into smaller bits. So that's myoglobin, 1 protein unit, right? And then we zoom into this. This is the binding pocket of oxygen, and this should look familiar to you now. That's this cutaway, right? So we zoom into this, and we have a veritable molecular Nanook of the North. We have a before and after snapshot of binding of oxygen, right? And this is grace of Max Perut's Nobel Prize work. And so we have a before and after snapshot. And now I have to teach you sorry, Albert's in the audience, but you have to excuse. I'm going to give you a 1-minute tutorial on transition state theory, right? So this goes back to 1920s with Michael Polanyi and Henry Eyring, and people were wondering, of all the possible degrees of freedom, there's a bit of magic in chemistry. Why does it always distill down to a few key degrees of freedom that chemists can pattern recognize, right? And so people were arguing a lot about this, and I'm going to color this. It's not, don't hold me to it, but this is to get across the main points, right? So imagine I want to convert my left hand into my right hand. That's much more difficult than this protein. Sorry, the protein is much more difficult, more independent degrees of freedom, right? So imagine I'm trying to do this. I simply can't do it, right? So if I want to do this, I would have to break my fingers. That's going to hurt. I have to put energy in, so axis is this way, right? I have to turn them over, and then at a critical point, like this kid's game, right? I don't know which is my left hand and my right hand, and you have a fluctuation coupling to a nuclear continuum that collapses the wave function, and I have the new structure, right? The question is, how do these forces get parlayed into just a few key modes? And at the end, my final movie, I think we're finally getting a handle on how you can map reaction coordinates onto just a few critical reaction coordinates, right? So given what I just showed you, you have this before and after snapshot. The critical point's supposed to be halfway between the two structures. So every chemist I know, this is the, so you can't see from that top right thing, you can't see what the structure is. But so let's say this is the oxygen here, my knuckle's the iron. When that bond breaks, it's a homolytic cleavage. The electron goes from the bond into the d orbital of the iron. The iron basically gets bigger and it pops out of plane. So it's this motion. So if you look at that, it looks like it's uniaxial motion along the orthogonal to the ring, right? What could be simpler? Halfway is the transition state. This is the one that we really think we nail. Okay, so I'll spare no expense to my demos. I couldn't find a plastic cup here. So let me show you the problem with this. If you think that, you're dead wrong. I would just apply a uniaxial force to this object, and you see it expands. You have off-diagonal couplings, right? That's Poisson's ratio in finite mechanics without boundary conditions, right? So what we showed in 2003, if you want to look the paper up, we showed that in order for that iron to move out of plane, there's some magic. Hopefully don't overuse that word, but there's really something quite interesting. In order for the iron to move out of plane, the heavy ring modes have to move to allow the iron out of plane. Those ring modes are exactly subharmonics of this protein, this fluctuation right here. Okay? So I'm not going to go into all the details, but we know that proteins are way too many degrees of freedom to sample all degrees of freedom, right? They have strong correlations imposed in the structure. And if you look at these structures, I defy you to figure out how they're wired up. And I'm just getting my last analogy to give you some sense of the interest in this problem, and hopefully don't overstay this particular slide. I know I'm going to be rushed at the end, but I want you to at least see where things are going in this field. So just to drive home the significance of this a little bit more, I have 10,000 degrees of freedom in what is our simplest example of molecular feedback that leads to a living system, right? So imagine I invite you to Hamburg, and you go to the Philharmonic whenever it's finished, and there are 10,000 seats, and each seat, there's a musician playing, it's an instrument. If you're to walk in, you hear this cacophony of sound with no sense, right? I kind of like that orchestra hum. But then if you walk in, the conductor taps his baton, and then you hear this beautiful music come forward, right? Well, what just happened? Well, the 10,000 degrees of freedom all agreed to be correlated through space, right? In biological systems, there's a correlation length scale we're looking for that's imposed in the structure of this protein. And you need to know the structure at the transition state to be able to control the barrier height. So the question is, what are the fluctuation and correlation length scales? My group's come up with this collective mode coupling idea to explain how biological systems are wired up. And in my book, we've proven it, but I can't tell you the exact motions and topologies. There's a kind of periodic table of biology waiting to be discovered, but it won't be elemental. It's going to be based on topologies to understand dynamics, right? The whole protein is involved in that structure, in that transducing chemical energy. Chemists right now, what we do, we heat and beat stuff. You know, we have one-dimensional control, and maybe we have asymmetric catalysts. Biology has charge, correlation lengths, local electric fields that can modify and polarizabilities. It's a multidimensional problem that's been highly optimized. We're just starting to learn how to control chemistry at the level of this machine's done it. So the question is this: what is this kayak, this molecular kayak doing? What are the correlation lengths? And I can come in and break a bond here and watch those forces be transferred into forces. And if I can see which atom is moving with which, I can figure out what the correlation length scales are and get an atomic basis to understanding biological system functions. Okay, so to see atoms in real time, what I'm trying to make a case for you, there's no other method to solve this structure function correlation biology, to understand biology really at the atomic basis set. This is where we're going. This is I think one of the grand challenges. And we're getting very close. For a while, I thought I was going to die before I saw this. I think I'm going to live, okay? And one of the reasons I think I'm going to live is because there's these things called fourth generation light sources, which can also now do this with X-rays, right? And their camera is 3 kilometers long. I'm actually have an office, well, my office moved over here, but I'm actually in Hamburg here for the XFEL. This is Spring 8, and Switzerland also has an XFEL. You know, the time resolution is now 200 femtoseconds for this. These aren't free, by the way. They're called free electron lasers, but, you know, these are billion-dollar facilities, right? And I have to say, a lot of what we're doing, I'd like to compete with these, to be honest, and save them for experiments you can't do with electrons. I'm going to give you a case that we can now, we've increased the electron source brightness that we're on par for many of the problems that you can contemplate doing on XPP. Okay, we're really there, and I'm going to show you some remarkable data we just got in the last month, after 20 years' work. Okay, so I was brought to many workshops to debate what way to go forward. Could we use electrons? And the thing you have to appreciate, and this is a key point in my talk, is in order to see structure changes, you have to excite approximately 10% of the atoms or unit cells in order to get above background. If you excite 10% of anything, it's not reversible. You're going to change it in some way. And so the challenge isn't hard enough that you have to get atomic resolution and femtosecond time resolution. You have to get all that information in a single shot. That's the challenge, right? And that's why brightness comes in. And that point was a bit missed. And so what I was told at these workshops is, yeah, it's very nice, but you're never going to get the number of electrons that you need, the current density you need to be able to pull this off with electrons because of electron-electron repulsion or space charge effects. And if you could do that, you're never going to be able to solve the T=0 problem. How are you going to know when the laser pulse gets there to trigger the structure change and when your structural probe is going to get there, right? It was not known how to do that. And then the other thing is, how are you ever going to characterize your electron pulses even if you could solve these other problems because there was no detector fast enough, much like the 80s for femtosecond pulses. How do you characterize them? Because you need that information. You need both this and this to string together to synchronize your movie, right? And so this was thought, not, you know, when we first started this, to be impossible. And I'm going to give you a progress report. In the last 10 years, we've solved all these technical hurdles, right? And so we're now down to 10 femtosecond time resolution and 10 micron picosecond resolution. So just for a historical perspective on who have come before us with electrons, and I'm talking only about structural changes where you can actually see atomic displacements, not just heating. So the first was Eubanks and Isharenko on the microsecond time scale. I don't show that. Gerard Moreau was really instrumental in getting me to Rochester. He promised me we'd do this. Turns out his first experiments using a street camera were mostly heating. They didn't have enough to really see structure changes. And then Ahmed Ziwell's group is in here. Here's a defining wall. The philosophy here is that you could get around space charge by just using a single electron. The problem is you have to have 10 to the 6 electrons to make an image, and you have to hit a sample 10 to the 6 times. And we have yet to find a system that you can do that and attain femtosecond time resolution and angstrom spatial resolution, right? So the big break, in my opinion, was made here. We cracked this picosecond barrier where we used high brightness pulses, and I'll show you how we solved the problem. And that got us down to 600 femtoseconds. We're now down to 200 femtoseconds, and within about another year or so at 10. And if you draw a straight line right here, this is when Dwayne Miller retires in the German system. And we'll be at 0 femtoseconds. This is this Knox, who's there joke. All right, so for the students, this is kind of fun for me to tell you because I survived this dramatic event. But yet, picture, I moved to Toronto, I moved my entire group to Toronto to do this experiment. My wife still doesn't quite understand, but we moved for this experiment. Right? And so we have you have startup money, we built a machine, my students build their own lasers, they build their own zero-jitter streak camera, they build the electron optics, and Brad Civic, who's one of my best students, comes into my office after 2 years of trying to measure electron pulses, says, this bleep bleep experiment will never bleep bleep work, right? And you know, I already sunk 6 years of my life into this or more, 7. Right, and moved everything. And he showed me in the back of an envelope that the theory we used to calculate the electron gun was incorrect. It couldn't get the asymptotic limit right? And so I remember this was one of the darkest moments of my scientific career. And then he asked me this classic question that all frustrated experimentalists ask, could he do theory? And so I said, yeah, sure, okay. And I was pretty depressed. So anyway, he did a great job. He used this tree code that was developed in astronomy to solve what effectively is exactly the coupled equations for 10,000 electrons. And we found something remarkable that solves the space charge broadening problem. I'll show you here. And he also came up with a really nice mean field approximation to calculate very accurately the electron propagation dynamics. Okay, so he gave one group meeting to show he could handle the Barnes-Hut code. We showed early galaxy formation, timescale 10 to the plus 15 seconds, very nice pinwheel formation. Changed the masses from stars to electrons, gravitational forces to repulsive forces. Boom. He gave this also famous group meeting, and I show you this slides, and you'll see the problem. At t equals 0, here's a 100 femtosecond electron bunch with enough electrons to do the job we want. You propagate just 0.2 nanoseconds. If you can see what's happening, you see the scale here, the scale bar, the pulse is broadening, which you expect from electron-electron repulsion, right? We had no idea it was going to broaden that fast. This is 2 centimeters of propagation. Our gun was 20 centimeters. He was right. We were never going to get this to work, right? And so you can kind of see, understand this calculation. You have a bunch of electrons. If you're moving with the electrons in the front see electron repulsion, a lot of charge behind them. They get accelerated. The ones behind them get decelerated. This is the space charge broadening. What was unexpected, if you look, with non-relativistic electrons, you maintain the space-time correlation, right? The high-energy electrons move faster than the low-energy electrons, and they just simply eventually sift out and form almost a perfect linear chirp. If we have chirp like this in optics, you just start to salivate. You know you can compress this, and I'm going to show you how to compress this. But when I left that group meeting, I have to say I was totally depressed for the entire weekend. I didn't jump off a bridge or anything, but on Monday I came back, and if you stare at this data, and this is a bunch of data we had, I distilled down to the main bits, right? There are 2 solutions to the space charge problem with electrons, right? The first solution, if electrons are broadening as they propagate, just don't let them propagate very far. The key answer was that the distance you could propagate is about 1 centimeter or so. Nobody had ever built an electron gun with 100 kilovolts in 1 centimeter. I have lots of funny stories about lightning and electrical storms in the lab. And then, of course, the other solution, which takes you a little bit longer, is to come up with some way to compress. And you can imagine if you have time-dependent electric field, this is a standard solution in high-energy physics. You can invert that phase diagram and temporarily refocus, and that's what we also do. And I'm going to give you a progression now of how we've solved and managed this technological issue. Okay, so here's the first movie. And I'm going to run out of time, like I always do. Whenever you have new technology, you should always do the simplest experiment first, right? And so you can imagine my group sit around drinking beers, what should we do first? Well, let's hit something really hard and make it melt. Well, that's not so far from the case. But actually, there's a little bit more to this. So I want to also give you another thought experiment from 1930s. There was a big argument between Born and Goeppert-Meyer about what the bound state of matter was under extreme heating. Okay, so let me walk you through this. If you read the papers, this is not the way the story is told, okay? But this is my version, right? So imagine I have a block of ice, and I'm watching it melt. Because I'm like Albert Stolo, I'm a physical chemist, and I have nothing better to do, right? So you know it's going to melt from the surface in, right? The other thing you all know, if you put a blowtorch and direct that towards the ice, it's going to melt faster, right? So now if you're a theoretician and you can do these kind of games, imagine I have a special kind of blowtorch that I could heat that material up so fast that no matter what theory you use to predict the phase front velocity, you would predict that the system should melt faster than the atoms could move, faster than the speed of sound, right? This is because they predate plasma physics. This is the experiment we did, okay? So there's a raging controversy when we did this experiment on another issue, but this is the one I'd like to tell you about, right? So we have a special kind of blowtorch. We have a femtosecond laser. We heat up polycrystalline aluminum at a heating rate of 10 to the plus 15 degrees per second, and then we just watched, right? And you don't have to do any detailed data analysis. You're going to see something. If I just walk you through the steps in the analysis, you'll see something remarkable. And this is one of these great stories. I have to tell you this story, and I hope I don't offend anybody, because there's going to be an application here, right? It's one of these great stories where you do basic science, you don't know what you're going to find, and there's something remarkable in just these first 4 frames, where it was the first to have enough diffraction orders to solve the structure, right? So if you look here at 500 femtoseconds after the excitation, you see these rings. That tells you have long-range correlations leading to diffraction, so it's a solid still. That's already solved the big problem in the literature at that time. Now you look at 1.5 picoseconds later, you see how those rings are getting dimmer. That's because the electrons are losing energy into lattice phonons. It's shaking more violently. You have less coherence at the underlying scattering wave vector. And so you get a decrease. And this is the Debye-Waller factor. We can actually tell you what the lattice temperature is, right? Now, the stunning result is here. Between 2.5 picoseconds and 3.5 picoseconds, you can see there's a little dim line there, and it's gone. This is the time when this thing basically collapsed from a solid into a liquid state, right? 1 picosecond, right? If there was sound effects for this movie, you would hear this wind roaring like a wind you've never heard before. Suddenly, the branches would all snap and break, and the system would collapse from a coordination number of 10 to a shell-like structure with an average coordination number of 10, 12 to 10. And you can literally see the shearing motions that lead to going to the liquid state, right? Why is that? When I tell my relatives this, I always get really kind of worked up, and they're kind of like, well, so what? And maybe you're asking the same thing, why am I making a big deal of this? Well, the so what is, rather than melting from the outside in heterogeneous nucleation, that would take 10 picoseconds, 10 times longer than what we observed. It's absolutely clear that this is melting from the inside out, and most important is because the time scale for this complete collapse is 1 picosecond, the nucleation sites can only be 1 nanometer big on average. Now, why is that important? If you ever have laser surgery in your lifetime, you may thank us for, or at least remember this, because they've tried to use lasers for surgery for 50-some years now, and they only use it for laser surgery where you want permanent damage, not healing. And the reason for that is you get cavitation. If you think about a pot of water boiling, you have to, laser cutting, you have to go solid, liquid, gas. If you think about a pot of water boiling, you get gas, the bubble nucleation sites that grow, and then violently collapse. That leads to shock wave and horrific damage. They killed a lot of people in the 80s. I had nothing to do with that. Right? And so this is what they do to you now if you have laser surgery, or if you have Da Vinci robotic surgery, which I've seen, this is what they do to you. We took what we learned about at the atomic scale of strongly different phase transitions. We developed a laser system with the same temporal profile as an impulsively driven phase transition, and we made it specifically to excite water, which we're made 60% of, and now watch this. And this worked way better than I could have dreamed. I knew this was going to be the fundamental limit for minimally invasive laser surgery, but watch this. Okay, this is how they cut you now. And this is our laser now with chicken skin. You notice no smoke. And we need Ursula's help to build a better laser. And you can see absolutely no smoke. The water's being super excited. The whole phase transition happens faster than even collisional exchange to the protein. We get entire proteins intact into the gas phase. And we show there's no ionization, radiation involved. 80 milliwatts is just 20 times the power of this laser pointer. And you see it just melting away the skin. And the key thing, and this is the first time by any method, bar none, you can now do surgery at the level of a single cell. That's one thing. But the most important thing is, okay, this is showing you longitudinally the absorption is confined to the depth of a single cell. We showed, and there's a paper if you want to check it out, this is the first time by any method you can now cut and do things without scar tissue formation. So if anybody's ever had nerve damage, I've had, you cannot do surgery for these poor individuals because the scar tissue compresses the nerve and makes things much worse. There's a whole bunch of things you can now think about doing. Anyway, so this all comes. It's a nice story. Had we gone in to try to make a better laser for surgery, we would have never figured this out. So I like this story of science doing something maybe important. Okay, so that was the first movie. I don't have time to show you, but this is reciprocal space, real space, and if you stare at this long enough, I play it for you. I'm not going to spend too much time. You actually can figure out that's the shearing motion of the corner atoms that is doing most of the talking. This is the first time you could talk about relative atomic displacements faster than diffusion. And so this is the first data point. We're moving towards proteins. And I know a lot of you are probably saying, yeah, this is a long way from proteins. Okay, so that's 10 years ago. Okay, so that was a third generation gun. This is our fourth generation gun. This is from Christoph Hebeisen's work. We had single shots. This gun has a hybrid wraparound lens. The whole gun went from 20 centimeters to 3 centimeters. This went to 2 centimeters. We even have a new gun that's only microns big, I could tell you about. This gun is 200 femtosecond time resolution, and it's increased the effective intensity by 10 to the 3 to 10 to the 4 over previous electron sources. The new machine I'm going to show you at the end is another factor of 10, and we have another factor of 100 to play with. And so all the movies I'm about to show you, when you see the quality and improvement, we have another factor of 100 to go with technology we already know and have a handle on. So how do we get the time stamping? So this was one of the first things I just want to show you. So there's a well-known effect called the ponderomotive scattering potential. This is a laser. If you apply an intense enough laser to an electron, it'll move it'll drift in the electric field gradient. And the question was, how big a laser pulse do you need? Well, we did the calculation, and the answer was 10 millijoules. And I'm just going to show you, this is the calculation, electron hitting a phosphor screen. We did the same tree code calculation. And come on. You're going to see, here comes the laser pulse coming in. And this is where we pinhole it. You can see just like a boat in water, leaving a wake behind it. Okay, so how well does this work for characterizing electron pulse propagation? And the reason this is really critical, if you remember the calculations, the electron pulse dynamics are very rapidly changing. So you need high space and time resolution. Okay, so watch this. That's a 90 femtosecond laser pulse that just flew by, and look at how stable that beam is. Huh? So I think you'd kind of figured out, I'll show you a little bit better presentation of this so you get the idea how we do this without getting into details. We can literally shoot a micron-sized bullet at another bullet and pick it out of the air, and you can kind of see like a bullet going through a lemon. You can imagine how you could reconstruct both the temporal profile of the electron pulse and find t equals 0. So we've improved the time resolution of street cameras by a factor of about 100 or more, probably 1,000. And the spatial resolution by a factor of 1,000. So you now literally can track the longitudinal phase space of an electron pulse as it propagates. Okay, so now to show you some actual data. Again, to remind you of the experiment, the sample sits here. This part I have to emphasize. The sample sits there. We're using electrons. This is the big challenge, and the dig I get from most people say, yeah, but you have to use electrons. And the samples have to be very thin, that's true. The samples have to be 20 nanometers to 100 nanometers thin. Mostly what my group does is nanofabrication. So we are experts now at nanofab, and Jason Dwyer is the guy, one of my first students who started this program with me. He figured out all the nanofab, how to make our molecular movie film. So you have to consider, in the experiments I'll show you, we have freestanding 20 nanometer to 100 nanometer film, and some of our cartridges look almost as big as my hand using silicon nanofab, where we literally have millions of time frames. And so everything now is the samples, and as it should be. So the machine physics is done. And I could walk you through a number of different experiments. Just to give you some insight of what you can do with this new tool is you have a frozen lattice, your laser pulse. There's other ways to do this. I'm going to go through what the standard method, pump probe method of doing this is. You come in, you perturb the system to some excited state potential, and then you watch how the atoms move in that potential. So in a single measurement, you can map out a many-body potential by looking at the atoms as probes, if you will, right? And so we did a whole number of different problems, and I'm not going to go into the details other than you have to have some degree of electron-electron correlation to lead to anisotropic changes in the potential. If it's a pure metal, gellium, it's isotropic, and we only see thermal effects. Once you see some anisotropic potentials where you change the electron distribution, that creates forces, you start seeing atoms move, and you can actually start thinking about things in an interesting way. And I'm not going to go on to all of these, but we've looked at aluminum I showed you. We looked at silicon, which is the poster child of non-thermal melting. We saw the first evidence for electronically induced nucleation phenomena, which is different than what was predicted. It was a surprise. We looked at gold. There was a long-standing issue in warm dense matter community. What is it, a loosely bound plasma? What is this long-lived state everybody saw that was just hanging around for picoseconds when they basically blasted close to fusion temperatures? We essentially put our hand into the sun several thousand kilometers deep, pulled it out and went, it's a liquid, right? So this is what we did with the gold. And then the bismuth, we actually had a situation where this thing went from an distorted phase center cubic lattice to a fully isotropic liquid in less than half a collision. So this was a case of ballistic melting, no collisions, right? So these are problems we've looked at, and we've also been able to use the electrons in an imaging mode so you can actually trace out field lines if you're interested in plasma physics. Please remember, I'm in the chemistry tribe, right? So we've done some physics, but I'm coming back now to the biology problem that I started. Now I want to tell you how well we're doing, right? So let me show you this problem, which is tantalite disulfide. This is a layered material with a slight distortion. You have a little bit more orbital overlap in the top layer, and you get a kind of corrugation. These always are layered materials. And so in real space, you see this in an STM. So you see a period doubling, and you kind of see this hexagonal kind of symmetry, if I can find it here. Right? So that's what you would see in a scanning tunneling microscope. And I developed a lab for undergraduates where you can see these kind of things clearly. Okay, so anything you see in real space, you can see in reciprocal space. And now I want to show you our, now you saw, remember the aluminum data and the diffraction? This data, you have to agree, is better, right? So the quality of this diffraction, to me, is really remarkable. We have literally hundreds of diffraction peaks, right? And if you zero in on just this one right here and look, that's scattering at low Q, that's the charge density wave. That's this in real space, in reciprocal space, right? And so now what you do is you come in, the electron density maps onto that charge density wave, right? Now you come in with your laser pulse, you perturb the electron density, the electron correlation effects are different. That's going to create forces that are going to lead to gradients, they're going to drive the atoms to new configurations, right? And so you can go with excitation, without excitation, and make a difference map, right? And I'm just going to show you, just to show you how good the data, the quality of the data is, we're just going to look at this one diffraction order, and we're just going to look at the data here, and you see blue is down. You see within 300 femtoseconds, just in these cutaway frames, the charge density waves disappeared. That's quite remarkable because the structure order parameter, if you think about the time scale it would take to move these atoms, that's the period of that motion, half period of that motion, right? And then I'm going to show you to give you an idea of the quality, but the surprise is we actually see an increase in coherence in the diffraction of the underlying hexagonal close black lattice. And this was a surprise, because normally you lead to greater disorder. So I'll just show you the data. One diffraction order, just watch it. So here comes the laser pulse. Here it comes. Wow, the charge density wave went down, and that got brighter. And you see that by eye on just one diffraction order. Now we can take all these diffraction orders, and we can average them, plug them into Toy Story, 3D Max, which is used for Toy Story, and animate what I just showed you. And so this is what's shown here. And we interpolated some of the frames, of course. But now you can get a really beautiful picture. If this goes, and here it goes. So you're going to see the charge density wave go down, this increase in the coherence. And then after, when these excited electrons lose energy to the lattice, you're going to see this go down. This is the Debye-Waller effect. Right? Come on. Right? And then it kind of, so you have this somewhat relaxed, smaller amplitude. It's not completely gone, charge density wave. But then you see as these optical phonons relax into acoustic phonons, which no longer match the structure order parameter, the thing relatches. And to me, that's even more remarkable. I mean, I was tortured with the Ising model for cooperativity in my many-body physics class, right? And so this is one of these beautiful examples of cooperativity you see at the atomic level. Okay, now some chemistry. Okay, so this is a wonderful material by Earring. It was developed, the Japanese, bless their hearts, spent enormous efforts developing photoactive materials to replace DVDs. I don't know how Erie came up with this, but this fluorine substitution here was a brilliant move. It leads to an electron withdrawing in that direction and creates a defect that causes the ring to close, right? So what happens is, and I'll show you, if you look here, there's 2 single bonds here and here. When the ring closes, you have a completely connected wire. And so just particle in the box picture, you go from small box to big box, the absorption spectrum becomes redshifted. So it's a beautiful example. Now you have a very strong absorption in the red. And so you can very clearly optically see when you have the ring open and ring closed form. The quantum yield is 100%, and I'll show you the data in a second. You excite in the blue, that causes that ring to close, and then you see this absorption. And you can, I mean, we have crystals that look like this. You shine light on them, and you can see the color change by eye, and you can pump red light here and push them back. You can open the ring, okay? So we've done femtosecond time-resolved crystallography. We've characterized the dynamics in situ, and people are just now starting to do this in third-generation sources just for absorption. We've fully characterized the femtosecond dynamics in the actual crystal, so we have the quantum state dynamics, and now we want to look at the nuclear motions. And the key message I want to tell you right now is in every single system we've looked at, the maximum peak power you can expose a sample to is 30 gigawatts, which kind of makes sense because laser optics usually damage at 10, right? So why am I saying this? If you want 100 femtosecond time resolution, even at exfels, your samples have to be micron to submicron thick. So there's virtually no difference in sample preparation conditions between electrons and X-rays. Okay, that's lesson number one. We've characterized the dynamics. There's 100 femtosecond, there's a sweeping of the wave packet and a shortening of the gap, and then you get this closing of the ring and absorption of the red. Okay, so here's the original diffraction. It's not bad. Here's after UV excitation with the ring closed, and here's us pumping it back with visible light. And we find that if we excite a larger fraction, something around 6%, where you have on average a neighboring unit also reacting, you actually change the dynamics. There's through-space coupling. There's structure changes that affect the barrier at the adjacent site. This is how nature figured out how to couple reaction coordinates. So this is a general property of, I'm sure, closed-packed systems. So it turns out molecular systems are much more difficult to do than strongly correlated electron lattice systems with the entire unit cells affected. So here, just showing you the data. We start, okay, here you can see, we're just reading this off the screen, boom. Now we're pumping back with red light, and then boom. And we have hundreds of time points in between, and we can cycle this to about a factor of 1,000 and collect the data. And then you can solve for what the structure changes is. We have already published this, and we have new data now. We've solved this. We're getting a very nice picture together. And what we compare, this is with Carolyn Morrison's group. We've taken Mike Robb's ab initio calculation for this potential surface using a cutaway model that's supposed to have all the secret ingredients. And what we find agrees very well with this calculation. You excite in the open ring here. There's a repulsive potential which drives the system close towards ring close. This is an example of ring closing with conserved stereochemistry. So there's no time for those groups to move around. So it screams in here, and then it doesn't go over the classic transition state. It rattles around here and then falls in, and you get the closed ring form, right? And we did a modal analysis. This is with Carol Morrison's group. And what I can tell you is the timescale we see corresponds to this half period of this 55 wave number mode, which brings these two carbon atoms closest together, and then it gets hung up, right? And now it's interesting because this involves the entire molecule, yet the ring closing is localized. This gets back to thinking about how does chemistry distill down to such a few simple reaction coordinates, right? And the problem in chemistry we have is we have a reaction coordinate like this with a barrier, right? We talk about motions that involve equilibrium fluctuations, and then we try to project that picture onto the crossing point where it's highly anharmonic. And so clearly, as this mode is being displaced, it's very strongly anharmonically coupled with more localized motions, which then close the gap. And we're just starting to try to feel out which motions are involved, but we're now able to get our first glimpse of the microscopic motions that govern a barrier crossing. Okay, this is the movie I want to show you, and I think I have 2 minutes left. Yeah? Okay, so I want to tell you, okay, this is my slant on chemistry. If you ask another chemist, they'll tell you this is not correct. But one of the big challenges in chemistry now is to get away from molecules, controlling the structure of molecules, and controlling mesoscale properties. They want to make molecular motors. You want to make bigger scaffolding to start to mimic nature. And so you want to control mesoscale properties. And so the simplest thing chemists can do is they make a molecule, then they take advantage of a crystal order packing parameter to arrange things in space that they can control a macroscopic property. This is Yamuchi's work, and it's brilliant. And so he developed this model, and I'm a chemist, and I can't even pronounce this for you. That's what it looks like. It turns out when you put this in a lattice at low temperature, it forms a charge order system. There's slight herringbone stacking of the molecules, like so, and that leads to charge order. You raise the temperature and get larger fluctuations. That leads to a metastable point, right? And what happens is now you have planar rings where you have electron orbital overlap, and you can convert a nominally or inorganic, highly insulating material into something that's highly conductive, right? It's a one-dimensional conductor. This is really interesting. And so the question are, what are the motions? And you use a standard transition state model, you'd say, well, it's just that bending coordinate. That's it, right? Now I'll show you the actual answer. Okay, so this is the new gun. This is our 5th generation. We're now up to 10 to the 6, nearly 10 to the 6 electrons per pulse in a 30 femtosecond pulse. Our time resolution is limited by RF jitter at 200 femtoseconds, but we have a fix, thanks to Daisy, to be bound around 20. 10 to the 6 electrons, when you include the difference in electron scattering cross-section, which is 10 to the 5th compared to X-rays, this is very close to LCLS performance in terms of what you detect on the detector. Here's the diffraction with our 4th generation machine. This is what the sample looks like. You can clearly see big changes in just the static temperature. Here's the new machine. We're getting diffraction up to 0.4 inverse angstroms. This is really remarkable. We're not crystallographers. We're just learning this game. My students didn't know enough. They cut the camera off. We actually have diffraction probably up to 0.2. I mean, this is really high resolution. The source is certainly good enough. And this is about a factor of 10 from proteins. So we're getting close. And I should tell you, we have 200 diffraction orders, of which 50 are clearly good enough signal noise to completely analyze. And you'll get an idea of this, right? The other big surprise is we've increased the radiation damage from electrons, which has limited the ability to study biological systems. It looks like certainly more than an order of magnitude, maybe 3 orders of magnitude in this short pulse regime. It's different than X-rays. Okay, so this gives you static, this is dynamic. So excitation, comparing X and with and without, right? And so you can clearly see there's some similarity. It's marching towards the final structure, which is the metallic phase. Look at the data. This is just taking 2 diffraction orders. That's extremely good signal to noise. That's amazing. I've never seen anything in time-resolved structural dynamics as good as this, and we can pull out a 400 femtosecond. Wow, for systems this complicated. I'm used to looking at proteins, looking at these things go crazy. Sorry, Steve, I'm overselling my work. I apologize. But this is good. We worked hard on this. Okay, we have over 50 orders of diffraction to analyze, right? Okay, and we can go out to nanoseconds and keep the same kind of resolution and see all the details. And we clearly see what Koshihara is very excited. He sees his hidden phase. He's very happy. I'm a chemist. I'm happy for different reasons. This is the dream we had over 20 years ago. This is raw data. Watch this. That's unprocessed raw data. That's beautiful. The peak heights are different. There's some displacements, but you can. This looks like pump probe data, but on 200 diffraction orders, right? So now you can easily imagine doing fitting the diffraction patterns to get the structures, right? Which is what we did. This was really interesting. So one of my guys decided to do a correlation analysis and just see, could he map all the structure changes onto a few coordinates? He fooled around with different coordinates. He did a random number sampling of different possible motions, and he found that all this structure, wiggling and moving, mapped onto 3 principal coordinates. And it wasn't the bending coordinate. And what happens is when you excite the electron, it goes to an adjacent molecule that changes the local electric field. The counterion feels a difference in charge. It moves. Right? It's the heavy atom. It slaves all the other motions. So it turns out we could map all the structure changes onto 3 coordinates on this hypercube to very high accuracy. And it's the slow mode that's the mode that's strongest damp that locks you into that final configuration. And so we're now starting to see which are the key modes that strongly modulate the reaction coordinate. Some are small modulation, some are strong. And you see who's directing traffic. So here's the movie. I apologize. We're not as good as others. So this is our first attempt at trying to... So, okay, you're going to see this 600 femtosecond overshoot. They're very small motions, right? So if you have to squint a little bit to see them. And then we're going to speed this up, and you see it just jiggles and wiggles. But you can get all the motions onto these projected, and they're all uniformly projected onto those 3 coordinates. Okay, so you can kind of see it as it's sort of jiggling and annealing out to the final metallic, fully conductive state, right? So you're starting to see the first glimpse of what slaving coordinates are involved, and these motions are the ones that also are determining the effective barrier height. Okay, so now where are we going? I want to now round the square, get back to my problem with proteins. What got me to Hamburg? There's this thing called the Relativistic Electron Gun for Atomic Exploration, or REGAE. So in the spirit of the Olympics, which just was held, it's stronger, higher, faster. Right? This is a fully relativistic gun. And I have to give credit to Jerry Hastings to first pointing out that this might be important. And this comes from the high energy physics community. So it's kind of interesting that there's a merger now between hydrology and chemistry and biology. I wouldn't call it a merger. Maybe it's a fixed marriage. I don't know, forced marriage. Anyway, this is what the machine looks like. The performance is 10 femtoseconds. This is the key. You put your sample right there. This has a rebunching cavity. So this, by the way, is high enough time resolution to see even the fastest motions, which is the OH stretch of water, for example. The key parameters, right where you put the sample, the transverse coherence is about 30 nanometers, which is comparable to the brightest field emission TEM, which is used for protein crystallography. So we're still ironing out the bugs in the technology, but this is, in the hydrogen physics community, this is pretty well understood, so we fully expect to be able to get there. Okay, so it's a pretty bright source. This is what I inherited. So I have to say I inherited a piece of historical German scientific landscape. This is the bunker for the first linear accelerator that Germany won the contract to welcome them back to the scientific community. It hadn't been used for 16 years, and they showed me this. What do you think? It's wunderbar. There's spider webs, there's paint peeling. This is the old control room. By the way, that's a 1950 era electric clock. That's Miller Group part number 001. So it's kind of fun to watch how this stuff all came together. So this is now the control room. It still has to be updated. We have temperature control tables for reasons I don't want to explain to you. But that's what the gun looks like. It's not so bad. It would fit around something like this, right? And the first shot gave us a beautiful electron beam. And there's things you can do to look at proteins. We're very close now. And if we can't do it with electrons, my group's also, I'll show you in a second, we've also worked on a cell that can actually mount up to 1 million protein crystals, which is what you need. You need 100,000 minimum basis to do protein time-resolved crystallography. My group figured out a way to self-assemble up to 1 million crystals in seconds. And so I want to show you this, though, but the other thing is we can also do solution phase. So we also solve the problem of nanofluidics. And this is brand new data. So this is a nanocell. This is Christine Mueller's work. What you're seeing here, which makes the hair on my arm rise, that's a nano gold particle you see undergoing Brownian motion in bright field imaging in a stem. So we have a 100 nanometer liquid cell with flow, right? Now watch the next. That's an amyloid fiber. We clearly have 1 nanometer resolution in liquid water, right? That's the thing that causes Alzheimer's, and you're seeing it actually move around and swim, right? And so now we're thinking, you can imagine, we can now look with electron probes at solution phase chemistry. If you looked at protein unfolding, you can even imagine now that we could stimulate protein unfolding, be able to watch a single protein unfold at some level of resolution, right? So we're getting there. Okay, and that's Christina's hand. It's a cheap cell phone camera. It's done in Canada, what can I say? Okay, so future direction, we can do solution phase, protein nanocrystallography. The REGAE machine is going to do the protein problem, but I also think we can look at live cells. So just imagine someday being able to look at cells undergoing cell division, watching this microtubule lightning bolt that leads to the separation of DNA, and watch the control of the centriome and how it orchestrates cell division, right? So these are the kind of experiments you can now think about. And we've also developed this megapixel array, which if we've fluorescently labeled proteins, you can see in seconds we can label with 75% fill factor almost 1 million crystals. So we're developing the technology to allow you to do film molecular movies. So this electron probes will compete, which I think is fine, but had we not done this background work, a lot of the technology we developed is actually being used by XFEL, and this chip is just one of the things. It's the solution to the solid target problem. And without a dedicated source, we could have never worked out these details. So there's also another feature. So I think it's going to be just like electron microscopes and X-ray diffraction, there will be synergies, right? So this is where everything's going. The future is clearly going to be bright. Brighter is better. And so in summary, the camera for the molecular movie is now in hand. It was done first with electrons. I showed you the very first grainy films, but you can see they're clearly getting better. You can see, I hope you get an idea from some of the science stories, the kind of picture you can pull together now when you look at things at the atomic level. And my point was, and I hope this resonated, that when you see things at this kind of acuity, your previous perceptions don't hold up often. And I think from a chemistry standpoint, we're really going to learn something deep and fundamental about why chemistry always goes down to such simple pictures that we can make recipes out of. Anyway, so this is, this is my REGAE music. You can hear it. Yeah! Yeah, so this plays in the control room all the time. Okay, so what I like about this is I think this is really an interesting time. So we just had the rover land on Mars, beaming back pictures of the landscape of Mars, so you get a feel for it. We literally now can beam probes into the transition state region and beam back pictures of the many-body potential that governs a lot of very interesting physics and chemistry and biology. And on that note, let me thank you for your attention. And I would just make one last comment is there's this Ultrafast Center for Ultrafast Imaging, and I'm the spokesperson, so I'm obliged to tell you this. So there are 9 faculty positions, and there are many PhD and postdoc positions for this new center that's going to take advantage of what I just talked about today with both X-rays and electrons. So on that note, thanks.
Are there any questions? Yes.
This EDO-TTF stuff was actually very interesting. I'm kind of amazed that you could do this on these sort of relatively delicate systems.
Yeah.
What was the excitation level?
We're exciting at most 6%. And then, okay, so the story was, the reason we did EDO-TTF, the 2006 paper, so this is kind of a can of worms. The 2006 paper said that this system was so poised to go metallic because there's a small fluctuation in the bending coordinate. So there's a reason I'm even explaining this, because it has to do with how you think about transition state crossings, even though solid state, you often don't do that, right? So the idea was that they excited 0.1%, and they optically saw a huge change of reflectivity, which they assigned to metallic behavior. It turns out that that was an excited state absorption, and then you didn't have all the information. The cranium was chronic to get the depth right. And so you don't see the onset of what you would call metallic behavior. You see it clearly in the diffraction. You get a one-dimensional wire. So you have to excite about 1%, and then you see the phase, this transition. But the other thing is, oh, by the way, the other thing is that excitation level, if you do this experiment at 1 kilohertz, you see no signal because the excitation heats the lattice and it doesn't cool. This had to be done at 10 hertz, which people could argue, oh, we could use this with 1 electron at a time. Good luck. It took us a few months to figure out that we had to, because it only cools from black body radiation.
Other questions? Yeah.
You said quite a bit about the sources.
Good point. So the funny thing is that my first slide, okay, this is getting back to my Canadian roots. We couldn't afford a detector, so we had this really cheap CCD camera. And so we had to average, my students were just crying. We had to average 100 time points because our detector was like 1% quantum efficient. So between the range between 1 kilovolt electrons to about 30 keV, an MCP and a fiber-coupled CCD detector, which is about 100 K, detects every electron. Above 30 keV, you've got to go like the 100 keV, and relativistic, we have to go to phosphor, and then in the relativistic case, the electrons blow through, so not to damage things, we have a mirror to collect the light and go on to a CCD detector. And we're marginally at signal-to-noise ratios of 2 to 1 for single electron detection, but we have new detectors that are coming from this HLL facility, hopefully in Hamburg, which will give us something, it's a threshold detector, which will give us 100 to 1 signal-to-noise on a single electron. And so there's even another factor of 10 in the detection, never mind sources, in terms of brightening up the images. So the detectors are hugely important. And in fact, the Swiss light source is the other one we're looking at, the Pilatus detectors.
Any other questions? You mentioned during your talk something, there is certain things you do better with electron diffraction and other you do with X-rays. So can you maybe elaborate on that?
Well, the one thing that might kill me, but we're going to try to do it with electrons first, is it may be that we just don't get enough spatial coherence for the protein problem. So we actually have beam time at the LCLS to do that problem. We're just at the ratty edge of being able to do, our coherence is about 20 nanometers and we'd like to have 30. So we might have to do that with X-rays, but then the challenge with X-rays is you need 100 different projections I want 100 time points. I need a minimum basis of 10,000 crystals. So we had to develop that solid target chip for the X-ray case, right? I'm pretty convinced we're going to do it with electrons, though. I mean, we have these. We have another factor of 100. We're just. I won't go into the details, but we can decrease the energy spread by at least a factor of 10, and we're there. I'm really confident we're going to be able to do it with electrons. Where you can't, where X-rays will really clearly clean up is in real space imaging on the femtosecond timescale, because you simply can't focus electrons down and avoid aberration problems. And so there, if you're doing coherence imaging, so you don't have to use Fresnel plates, that's where it's going to be great. So if you want to take a snapshot of liquid water and see the hydrogen bond network, that's where X-rays are going to work. So it's kind of interesting. So in the static world, X-rays win in reciprocal space imaging. No, people do mostly X-ray diffraction. In real space, it's electrons. They're at the atomic level now, right? So the problem in the time, when you're looking at the time, taking advantage of the time structure and high time resolution, it's going to be the opposite. X-rays are going to win in real space imaging, and electrons I believe, are going to win in reciprocal space.
But if you want to approach a problem very often, you will
have to use.
I want everything, right? I mean, you want to be a little bit electrons and a little bit X-ray, and then finally you get down to the groups.
I strongly recommend people do electrons anyway, if nothing else, to debug your system before you get X-ray time. I highly recommend it.
Any other questions?
There's one up there. We're working, so I don't want to give you the impression I do everything, but we actually are collaborating with Florian Gruners on a Wakefield accelerator, and the relativistic electron gun is going to be a probe. People don't know the gradients, so you have GeV per meter field, so in principle you could make a Wakefield accelerator that would, rather than going from 3 kilometers, you go down to like a few meters and get the same kind of energy to go through an undulator, and away you go. The laser system is very expensive, so maybe one could argue the price will come down for these kind of sources. My own feeling, I lost 2 years of my life on laser-based particle acceleration, and it may be possible, it's decades away, because the inhomogeneity in the fields just are going to be really tough. But anyway, we're about to map out, imagine you bring the probe in and you look at the Wakefield source and plasma, and you change the timing, you can probe by looking at the kick it gets, and try to figure out what you need to do to get a uniform acceleration. So that's another way to go, and there's great hopes, and Daisy is putting a huge program together, and our group's actually involved both in the injector. We're involved in the timing. We've actually solved, so there's another problem I don't tell you about, but the time synchronization has to be a few femtoseconds, right? So our system is actually being used to add different phase lock loops to get the time synchronization. So those problems being solved, the Wakefield accelerator could give you a nice compact X-ray source. So it's possible, but it's going to be a long time. The electrons, by the way, are dirt cheap. It's the detector that's expensive.
And the laser.
The laser's coming down.
Any more questions?
You mentioned very short electron pulses.
Not exactly. I have some ideas. So I think it's not entirely a mistake, but I think the problem isn't as bad as the people thought. They simply took X-ray damage values, there's radiation damage, and if you think about when I ionize with an X-ray photon, the emitted electron has hundreds of EV excess energy, so you generate secondary electrons. Many hundred energy electrons move very far from the ionization source, so when they trap, you've got a big field that accumulates and eventually strains the crystal, and that leads to the radiation limit that people think is what's limiting spatial resolution with X-rays, right? So the same thing was thought to occur with electrons, but when you have knock-on damage with electrons, the electrons that are emitted have a few EV, and they only go a little ways, and they will come back. And if you just if you do things fast enough, the amount of distortion you get is small on the time scale that we can probe. And so we've done some probes now, we use the electrons directly. We can hit crystals for months and not see any changes. This is the number I came up with. We can now detect changes, but it looks like we're at least, order of magnitude better. And that's all to get to single molecule reconstruction, people typically get 1 electron per angstrom squared dose limits. And now it looks like we could do 10. And that's all you need. So maybe it's not as good as I think, but it's certainly much better. And you don't need much to get to the point where you can talk about single molecule reconstruction.
I mean, one of the motivations people always say is that that the dynamics of the proteins is really important also for the drug development. And so traditionally, they only looked at static structures. If something docks on, then it should work. And then they implemented the drug, and some of them worked, and the other one didn't. And they kind of think it's because there is a dynamic going on that actually prevents them from really doing what they expected it. Did any of these time-resolved studies already resolve some of these issues?
No, because there aren't time-resolved studies on what are considered to be important drug targets. So 60% of the current drug targets are membrane-bound proteins, which are called G-coupled receptors. They're the ones that control traffic in and out of your cell, and those are the ones that lead to disease states. So anytime there's a breakdown in cell division, it tends to be one of these proteins that a mutation is affected, and so there's a huge effort to try and get these structures. Any hook will help, and these as you would know, nature doesn't give up her secrets easily, and these systems don't grow crystals well. And so one of the great hopes is that people can get protein nanocrystallography to work and at least get static structures. They can try to understand what motifs, they don't know how they get in, but what motifs may actually at least be possible, and that limits the combinatorial approach. They basically just do monkeys and typewriters. I mean, yeah, they have a static structure, and it's always after the fact. There's no real rational design happening, in my opinion. Don't tell my chemical biology friends that, but they get a kind of idea, and they just run a whole series of possible drug targets, and they screen them, and that's how they do it. Just to give you an example of how the dynamics is going to change, if we can actually get to a point where we can do dynamics on a system of relevance, just oxygen going into a diatomic molecule, oxygen going into myoglobin, on a static structure basis, it shouldn't go in. It's a 30 kcal barrier. You should not be alive. And so just as that as a testimony, I think once you can understand, probably what will happen is people will come up with drugs that have sort of characteristics of a protein, like half scaffolding, that'll help assist the drug delivery once we understand the dynamics. So it's finding topological similarities to help you drug deliver.
I think that's a good point to close. You know, I think that's, thank you very much.
Yeah.